Now I'm going back to that data that I showed you. It's going to be 20 days, consecutive days, was actually in year 2000 for the Microsoft stock. And I'm computing maturity as 20 over 252, where 252 is a typical number of working days on Wall Street in a year, in a calendar year. So that's about 0.08. So I'm going to use 0.08 initially for time to maturity. And now I want to estimate sigma. My data is the stock prices, but actually, since sigma is the standard deviation of the logarithm of the difference of the logarithm of stock prices, that's what I'm going to look at. Logarithm of daily stock prices, the differences between two consecutive days. I'm going to call that y of I, or y subscript I guess, if I use this notation. And then I'm just going to use my standard estimator for estimating standard deviation of the data, the standard error, which is just the square root of 1 over n minus 1, and here is 20, of the square differences of your data minus the average of your data. So yi bar is the average, the sample average of your data. Okay, you can just compute the sample standard deviation, and you get a number, something like 0.02. But this is daily volatility, and if you are going to compute everything in annual terms, I have to translate this into annual volatility. How do I do that? Well, the annual standard deviation would be the daily standard deviation times the square root of the number of days. Okay, because this is Brownian motion, this is how it behaves. Standard deviation gets scaled by the square root of time. So I multiply by the square root of 252, which is this. So about 0.32%, which is what I used also in my binomial model. Okay, so that's what I'm going to use in the Black-Scholes formula. I will also use 55, and at the initial time I'm gonna, for the strike price, at the initial time I'm going to use this for the stock price, and the interest rate is 0. Except I'm cheating here somewhat. Where am I cheating? Well, when I compute this estimate for sigma, let me go to this data. What I'm doing, I should really pretend I'm sitting at this time 0, right? And I don't see the future, right? When I start doing hedging, I don't see the future. But the way I computed this estimate of sigma, actually I used this data in the future. I found the sample standard deviation of my future data. You can't really do that, right? But I'm trying to see whether under the best conditions, which is when I can estimate sigma pretty well, whether I can get a good hedge. Right? So the quality of my hedge will depend on how well I estimate sigma. And here I'm cheating by using the future data to estimate sigma. In reality, maybe I would have used 20 days before this, or more than 20 days. Now it becomes a question how exactly you estimate volatility. In fact, as I told you before, maybe you wouldn't use stock data at all. Maybe you would just imply volatility from the prices of liquidly traded options on well, maybe this is a liquidly traded option, but maybe you would just use implied volatility to do your hedge. Right? You compute the implied volatility. But here I'm trying to think of as starting from the scratch and just using literally believing in my model and estimating somehow sigma. Alright, so we took 0.32 for sigma. Then what do? I compute the Black-Scholes price of the option using the Black-Scholes formula and the data and the sigma that I estimated, and I get 2.27, and I'm going to assume that I actually sell the option for exactly this much. Okay, otherwise there will be some difference that I will have to include in my profit loss. Let's assume that I actually sell the option exactly for the Black-Scholes price in my model. Then I compute the delta of the option at time 0 using n of d1. I get 0.5629. Okay, so I have to, which means that I have to hold long, have to buy 56% of the number of options that I'm hedging, 56% of that number in terms of the number of shares that I have to buy to hedge the option. As usual, I'm assuming if it's only one option, I can actually buy 0.56 of one share of the stock. Right? So I'll assume I can do that. And this is going to be less, this amount, 2.27, is going to be less than what I need to buy this much. So I have to borrow, with the call option you borrow, when you are hedging it, I have to borrow delta 0 S of 0, which is the amount that I need to buy delta 0 shares, minus what I get for the option, which is C of 0. I have to borrow that difference. Okay? So I borrow that difference, and then I go to the next day, and the next day it happens that the stock price is 55,375. And now I want to compute the new delta because I want to rebalance my portfolio using the Black-Scholes theory to continue my dynamic hedge. Okay? And here it's theoretically consistent to do that, unlike repeating static hedges, let's say with the futures contracts or with those bond portfolios. Here this is dynamically consistent. My theory says, yeah, this is what you need to do, just to rebalance using a new delta. So to compute the new delta, I have to use the new stock price. I have to use the new time to maturity, which is now 19 days remaining over 252 in terms of years. What is going to be my new value in my hedging portfolio? It's going to be my initial value, which was C of 0. And then it's going to be the delta of 0, which is the how many shares I hold, times the change in the stock price. So I have all these numbers I can compute, and my wealth goes down from 2.27 to 2.16. My replicating portfolio goes down, which is natural because the stock actually went down from 50. It was more than this. It went down, and the call option goes down if the stock goes down in value. So that's why my replicating portfolio also goes down. And in fact, okay, and it goes down, and then I continue like this. Then I compute delta of 1 when I have S of 1 and T minus 1, and that's going to go down too because I have to hold less shares if the value went down, and it goes down from 0.56 to 0.54. So I have to sell the difference. Okay? I have to sell the difference. So I sell the difference, and I just put the money in the bank, just reducing the money that I borrowed. And then my X of 2 is going to be X of 1 plus the new number of shares during the second period, during between day 1 and day 2, and change in the stock price during that period, and it's going to be 2.2 basically. And I continue like this. All right, I'm continuing like this. Okay, I'm ignoring here a bid-ask spread, the transaction cost. I'm assuming that I can do this in a perfect market, and I put interest rate to 0. So I'm a little bit ignoring also I'm also ignoring the interest rate. But in any case, in that situation, my wealth would go from 2.27, which was the Black-Scholes price of the option, then it goes down, then it goes up, and eventually if you do the computations, it goes to 13.66. Okay, so this is, you sell the option, you use all the money that you received to start this hedging portfolio. You end up at the end with a total hedging portfolio value of 13.65, and you have to pay this 68.81 minus 55, right? So your total profit loss is the difference, 13.8125. This is what you pay in the option payoff, loss in the option, and minus what you have in your hedging portfolio. It's about 0.15, 0.16. Right? So while the loss without hedging would be, I said before, it's almost $14, but not quite. It's 13.81 minus the what you get for the option, which is about 11.54. So you reduced by a lot. You reduced by a lot your loss by doing this hedging, even though you are only hedging once a day and not continuously. Okay, maybe it would be not so good if you introduce a little bit of positive interest rate during that time, and if you account for transaction costs. But if the transaction costs are not large, it wouldn't be much different from this. So you do reduce the cost of hedging, the cost of selling the option, the risk of having to pay this difference. So it works reasonably well, even though there was kind of a relatively high volatility during this period. In 20 days, the stock price actually went up quite a bit, more so than usual. Nevertheless, the Black-Scholes model gives you reasonable hedge. Okay, it's not perfect, but it gives you a reasonable hedge. Now, of course, it could have happened that the stock price went down below 55, in which case you don't need any hedge. In fact, you would lose money on the hedge, and you would make more money if you didn't hedge than if you did hedge, if the option turns out to be out of the money. But you know, hedge is an insurance. You buy insurance for the worst case scenario, and if you don't have an accident with your car, then then you lose the premium that you paid for your insurance. So in practice, it's not that option traders are going to start doing this for every single option they sell. They will hedge it, try to hedge it completely, put all the money they receive from the options into the hedge. I mean, they wouldn't be trading options if that's what they want to do, if they want perfect replication and be at a zero profit loss at the end. Okay? But they may want to worry somewhat about the risk to which they are exposed, and somewhat keep that risk under control. So we are going to talk about that in the next set of slides. It's the similar idea as with the bond hedging and futures hedging, especially with the bond hedging and duration and the convexity, where you try to keep the sensitivities of your portfolio low, sensitivities with respect to the underlying random factors. But here you completely kill the sensitivity theoretically, right? You do 100% replication, 100% hedge. In practice, you don't really want to do that. You just worry about your global portfolio being not too sensitive to the potential movements of the underlying random factors. Okay, that's it for this set of slides.